Okay, stop. Okay, it was here. Now it's working, no? Okay, thanks. So I was saying that with only 3 parameters, you have your chemical composition, your chemical equilibrium composition completely determined. Okay. So this is the good point of chemical equilibrium. So let's start by having an example of a planetary atmosphere that is extremely hot. This is of an ultra hot Jupiter. This is the typical temperature profile for the so you have in the y-axis the pressure, here in the bottom of the atmosphere and up in the top of the atmosphere, and here you have the temperature. Just notice that here we are dealing with temperatures of 4,000 Kelvin. Okay, so this is the an ideal place for chemical equilibrium to be valid. And when you just compute the composition of this planet, here you have in the solid lines the abundances. Here you have in the x-axis, this is the mixing ratio. So on that side you have abundant molecules and here less abundant ones. So solid lines correspond to disequilibrium. So they are computed taking into account different disequilibrium processes, and the dotted lines correspond to chemical equilibrium. And you see that the agreement is almost perfect. So the conclusion from this is that in very hot atmospheres, chemical equilibrium should be a super good approximation. So we can use it to predict very confidently the chemical composition. But not only you need super ultra hot atmospheres. Only if you go to an atmosphere that is relatively warm, not dealing with thousands of Kelvin, but with hundreds of Kelvin. This is a warm Neptune. So this is the temperature. In here you have the order of hundreds of Kelvin, and you do the same exercise. You see that chemical equilibrium here is the same. Dotted lines correspond to chemical equilibrium and the solid ones to disequilibrium. And you see that for the bulk of the atmosphere, still chemical equilibrium is a very good approximation because it predicts relatively correctly the abundance of the main most abundant and stable species like water and carbon monoxide and molecular nitrogen. And then for others, you start to see some deviations. Normally, in the bottom of the atmosphere, the agreement is almost perfect. So the conclusion is that in the bottom of atmospheres in general, chemical equilibrium is going to be valid. And when you start to go up, there may start to be deviations, and that depends a lot on the planet. Normally, the cooler the planet, the greater will be the deviations. Okay, and this to compute a more realistic view of the composition, then you need to include these disequilibrium processes. Okay. So, an ideal, so an example of how models may help observations, I will give you now, and it's provided by this chemical equilibrium. So these chemical equilibrium are very good, as I show you, for ultra hot Jupiters, and they allow to predict very accurately the abundance of the different species. So this was used, for example, to start this chemical equilibrium calculations were run. There were some predictions that, for example, atomic iron or ionized iron or other metals will be very abundant in certain type of atmospheres, and then the observations confirmed this prediction from these chemical equilibrium models. Okay, this is an example of the first detection of iron, atomic iron, and it was done with here in the telescope in the Roque de los Muchachos. So this is a basic picture of what is the main state of metals depending on the temperature. Okay, so you have here different metals, different elements, and here in the y-axis the temperature. Depending on the temperature, you may have that at low temperatures most metals will be in condensed state. At very high temperatures, most metals will be as ionized atoms. And in between, we may find neutral atoms and molecules, okay? And this depends a lot on each element. This transition is very different depending on the element, okay? For example, if you are in an atmosphere that has this temperature around a few above 1000 Kelvin, you may expect that some elements like aluminum, calcium, titanium, and scandium will be condensed, but others you expect to find them in the gas phase as neutral atoms or even molecules, okay? And you can do the same exercise for a different temperature. If you go for this other temperature, you expect that some elements like sodium and potassium will be mainly as ions, as neutral, as cations. But for the rest of the metals, you don't expect the cations. So this kind of exercise are very good to predict in which state will metals be mainly, okay? And this will help a lot then to prepare the observations or to see what will be found. Okay. I was saying that in this yellow part, you may find either neutral atoms or molecules, and this depends a lot on the element. Okay, there may be some elements for which the element will be mainly atomic, and others for which it will be mainly molecular. And this, as I told you, depends a lot. For example, in the case of titanium, you have here which is the main reservoir of this element as a function of temperature. At very high temperatures, we have the ionized titanium, then neutral, and then we have a certain temperature range where titanium monoxide is going to be very abundant. And this is the reason why this guy is widely observed in exoplanet atmosphere, because it takes most of the element, okay? But if you go to another, for example, aluminum, we still have this transition between ionized aluminum and neutral atoms. And then at lower temperatures, we start to have some molecules. For example, we have here in blue aluminum monoxide, which has been detected in several hot Jupiter atmospheres. But the funny point is that we have molecules that are predicted to be even more abundant than aluminum monoxide. For example, aluminum hydride or even aluminum hydroxide are predicted to be much more abundant. And these are a good case in which these models can help then to test through observations, okay? So in the case of aluminum monohydride, there is spectroscopic data. For the other guy, there is no yet spectroscopic data, so this is a good target to look at, okay? Okay. So all this was about some info about chemical equilibrium. Now let's start to speak about what happens when chemistry is slower. So there start to be other processes that start to compete or be even faster than chemical processes. That usually these are hydrodynamics or dynamics of the atmosphere or photoprocesses. Okay, when these start to be fast enough, they may drive the chemical composition out from equilibrium, okay? So basically, to start to describe this, the most simple model you may build is a 1D model. So in the vertical direction of the atmosphere, you just describe what happens in a column, in a vertical column of the atmosphere. And basically, the simple equation to solve is the equation of continuity, which contains terms that take care of the production and loss of the different species. And this production and destruction and formation may happen through chemical reactions or photoprocesses, basically. And then you have to include also some mixing that occurs in this vertical direction, because this will have an impact. Okay, so this is basically the way these models are constructed. And here I will focus on these three main items that may drive the composition out from equilibrium, and there may be others, okay? We have on the one side the vertical quenching, also horizontal quenching may be important, and photochemistry, of course, okay? And then there may be others like induced by cosmic rays or flares or other stuff that may even weathering or exchange with the surface. There may be other processes that may drive the composition out of equilibrium, okay? But I will focus on these three. So let's start with vertical quenching. So this is a very important process that explains many observed things in exoplanet atmospheres or even in our solar system planetary atmospheres. So the first time it was proposed as an important mechanism was by the observation of carbon monoxide in the atmosphere of Jupiter. So in fact, the prediction from chemical equilibrium is that in the visible atmosphere, the abundance should be super low according to chemical equilibrium, but then the observed abundance was much higher. And the interpretation was that there was a phenomenon called mixing, vertical mixing, that bring the molecules from the deeper atmospheres up to the observable atmospheres, okay? So this was the first time this was proposed, but this process explained many observed things in exoplanet atmospheres. For example, so here an important concept is which is the quench level, which will be the level in which this the rate of the mixing is equal to the rate of the chemical reactions. So below chemistry is faster than dynamics, and above dynamics is faster than chemistry, okay? So you have to identify which is the quench level, because this will be set, which will be the abundance that will quench above, okay? So as I was telling you, a nice recent example of this phenomenon happening is the recent detection of phosphine in a brown dwarf. This behaves very similarly to the case of carbon monoxide. In this case, the chemical equilibrium abundance that is plotted there as dashed line in the observable atmosphere is super low, but the only way to explain the observed abundance is that there is vertical mixing bringing abundant phosphine molecules from the deep layers, okay? So this, as I was telling you, is a very important process in general in planetary atmospheres, okay? And to properly describe this theoretically, you have to describe well which are the chemical reactions forming and destroying each species, and you have to have a good estimate of which is the strength of the vertical mixing, which is not obvious because you cannot predict that from first principles. So now I will now turn to photochemistry, which is also becoming very popular recently, mainly because the detection of sulfur dioxide in a hot Jupiter atmosphere with the James Webb Space Telescope. So this was, or this is claimed to be the first molecule produced by photochemistry unambiguously. Okay, so this is photochemistry is the only way to explain the observed abundance of this guy. Okay, the detection seems quite clear. And in fact, if you go for if you do some disequilibrium model, including the photochemistry, in fact, you see and you predict that indeed this sulfur dioxide in the blue curve is enhanced in the upper layers of the atmospheres due to photochemistry. The process that explains this basically is the photodestruction of H2S. That is the main reservoir of sulfur in the atmosphere, but when you go up, it starts to be photodissociated, and at some point, these oxides start to be produced. So the main drivers to form the main reactions that form this SO2 are these two reactions that involve sulfur monoxide as a precursor, which in fact, sulfur monoxide is predicted to be even more abundant than sulfur dioxide, okay? So this is also a nice prediction from the chemical models that at some point will be nice to test. This SO2 has been the first unambiguous proof of photochemistry happening in exoplanet atmospheres, but I'm sure that in the near future there will be more examples. One possible more example when it concerns phosphorus. If you go for a warm atmosphere, you have that phosphorus maybe must be mainly in the form of phosphine in the deep atmospheres, but at some point it will be photodissociated because it photodissociates very easily, and you may start to convert this phosphorus and will produce mostly phosphorus monoxide, okay? So at some point, I think there will be more examples of species that are proofs of this photochemistry, and observation at some point must be done to prove that, okay? So that about photochemistry. Now we'll speak a little bit about another process that is horizontal quenching, that also is very important in exoplanet atmospheres. Okay, so when we look at these problems some years ago, basically we were focused on hot Jupiters, And hot Jupiters have a very peculiar characteristics. Well, normally they are tidally locked. They have huge contrast of temperatures between day side and night side. And basically, the dynamics of the atmosphere is dominated by a equatorial jet, okay, that circumvents or surrounds the planet, okay, given orbits. So we took advantage of this property that the dynamics is dominated by this equatorial wind and constructed a very simple model. So basically we constructed a time-dependent 1D model that was moving around the equator simulating this wind. Okay, we call it this a pseudo 2D model because we were not taking into account properly all the 2D characteristics, but this, if the equatorial jet indeed dominates, this should be a very good approximation, okay? So this allowed us to investigate, to go beyond the 1D direction and to investigate what happens with longitude, okay? So basically, what we found is that there are interesting effects. Okay, I will show you here a movie. Basically, here in this side, you have the movie will show what is the chemical composition as a function of the longitude. It will go from the substellar point, which is one of the hottest, and it will go through the night side and come back. Okay, so we will see what are the predictions from chemical equilibrium and from our pseudo 2D model that takes into account the vertical mixing, the horizontal mixing, photochemistry, and all the disequilibrium processes we can deal with. And we will see what are the difference between the predictions from chemical equilibrium and the disequilibrium model, okay? I will, because there are many species here, I will tell you just to focus on methane, which is CH4, which is the red curve, okay? To see what are the differences. Sorry. So let's see if this works. Okay. So basically, we are moving from the day side to the night side. You see here that methane, when you enter into the night side, the atmosphere gets cooler, and methane, according to chemical equilibrium, will be strongly enhanced, even will become more abundant than CO. But here, when you look there, you see that methane almost does not move. So does not react to the variations in temperature. Okay? So according to chemical equilibrium, you expect great variations of the abundance because the temperature is varying a lot when you go from the day side to the night side. But according to the disequilibrium processes, these variations are very much reduced, okay? This is pretty the same, but so in a different way. So here you have like this kind of spaghetti curves where you see the variation of the abundance of the different species as a function of the longitude. So going from the day side to the night side. And you see here that according to chemical equilibrium, most species experience great variations of the abundance, but when you go to the pseudo 2D model, these variations get suppressed. Okay, so the main lessons from this kind of models is that the abundance get homogenized quite a lot as a function of the longitude. Okay, so this is one of the main and the abundance at which they quench, horizontally quench, are those of the hottest points of the planet. Okay, so normally the chemical equilibrium composition of the hottest point of the planet, which should be close to the substellar point, but not exactly, should be the ones that will contaminate the rest of the atmosphere, okay? The homogenization is very molecule dependent. There are molecules for which the homogenization is complete, almost complete. There is quite uniform abundance. Others may experience some variations, okay, because they react more to photochemistry or to other processes, okay? Another lesson is that this homogenization is very temperature dependent. This will be much more pronounced when you go down in temperature than when you are up. So normally the lesson from this is that if you want to find some differences in the chemical composition between the two terminator points, between the morning and evening limbs, for example, you better go to hot planets, because in cooler planets, in principle, the prediction for models is that the composition should be very much homogenized. So you should not expect great variations in the chemical composition between these two terminators, okay? And then there were other articles investigating on this approach for other planets, but basically these are the main conclusions from this kind of models. Okay. So as far as I know, this observationally, it has been attempted to find differences between these morning and evening limbs. But as far as I know, the main differences that have been found are due to temperature. So there are some difference in the temperature because morning should be cooler than the evening. And but as far as I know, there have not been no evidence, observational evidence of a chemical composition being different between the two terminators. Okay, this is very challenging observation. So I mean, even if the differences are there, they will be really difficult to characterize. So now I will go for the second part of the talk, which basically is trying to answer two questions. The one, what I was telling you, is whether this disequilibrium composition affects the temperature or not. So we will go for it, okay? So the motivation for investigating this in exoplanets was the case that we have here in our own Earth atmosphere, the case of ozone. Ozone is a very, very good example of a case when disequilibrium chemistry impacts the temperature, okay? Ozone is produced by photochemistry, so in chemical equilibrium, the abundance should be fairly low. It's produced by photochemistry, so through this set of reactions by the photodissociation of O2 and then the three-body recombination to form ozone, and then these other reactions that close the cycle. So clearly, this is a molecule that is formed by photochemistry, and it has an impact on the temperature because it absorbs very efficiently in the ultraviolet and produces this temperature inversion, okay? So the idea was to investigate when similar cases may be found or not in exoplanet atmospheres. So for doing that, what you have to do is to couple, these are the typical different types of models to describe a planetary atmosphere. We have like radiative convective models that basically compute the temperature as a function of the altitude. You have the 3D general circulation models, and you have chemical models. So to answer that question, basically what you have to do is to couple these two models. Okay, you don't describe the hydrodynamics. That is of course very important, but at some point you have to live with approximations. Okay. So the idea is that basically the temperature is determined by the opacity of the species that are in the atmospheres, and whether the abundance of these species is controlled by chemistry. This may have this interdependence. Okay, so chemistry control the abundances, the abundance control the opacity, and the opacity controls the temperature. Okay, you have this kind. So you have to solve simultaneously the temperature and the equilibrium and the chemical composition. Okay, so for doing that, you have to couple these two models. I just put a message here because this kind of models, it starts to contain a lot of data. Basically, the type of data you need to build these models is you need a thermochemical data, you need a reaction network, you need then UV cross sections to describe the photochemistry, and for the temperatures, you need these line lists in the visible or infrared that are the ones that set the opacity. Okay, so you need like a lot of data. For most of them, you can take it easily from databases. For others, mostly in the case of the reactions, you have to go one by one looking in the literature. So in my case, this took me quite a lot of time to build the chemical network. So basically, the conclusions from this study was I applied this, or I focused on typical planets that are observed, but basically they are ultra-hot Jupiters, or warm Neptunes. And here in this plot, you have the pressure in the y-axis and temperature here, and you have in the dotted lines correspond to a case in which you compute the temperature at chemical equilibrium, and then you let it fix. You don't allow that to vary. So you don't take into account the self-consistency between this equilibrium and temperature. While the solid curves correspond to the case in which you take into account this interdependence, okay? And you see that first for the ultra-hot Jupiter, there is almost no difference no, and this is expected because the chemical composition is already in chemical equilibrium, so you don't expect. So chemical equilibrium is a very good approximation to compute the temperature, and then you don't have to worry about this equilibrium. When you go to cooler planets, the differences are not very large, are at most 100 Kelvin, okay? Instead, in the case of this HD 209, which mainly the difference is due to titanium monoxide. But there is a warning message here because in the chemical equilibrium or disequilibrium, the abundance is very different for titanium monoxide. But there is a warning because titanium monoxide, the photochemistry is not known, in fact. So it's in the model is assumed. Okay, so there are big uncertainties concerning that. So basically here, this was a bit frustrating for me when I did the calculations because I was expecting to see more differences, but there were not much differences. And the main reason for that is that the main species that control the temperature in these hydrogen-dominated atmospheres are water and CO2, I would say. Okay, and the abundance of these two guys are very stable, are not much affected by this equilibrium. So as long as you have these two guys with uniform abundance are not very much affected, you will not find much differences in the temperature, okay? And then I asked to myself, the other question was that whether because there is an interplay between temperature and chemical composition, so this equilibrium composition may affect the temperature, but if the temperature is affected, this will in turn affect the chemical composition. But the differences, because the difference in the temperature were not that large, here the difference in the chemical composition also is not that large. So the message from this is that you may live with a model in which you are not worried about this interdependence between temperature and chemical equilibrium and chemical composition, okay? And then I turn to other planetary atmospheres, trying to find some examples where this may be an important effect. And then I focus on secondary atmospheres because the previous I talked you were mainly hydrogen, primary atmospheres dominated by hydrogen. But then if you go for secondary atmospheres that from the observational point of view are not very much characterized, you may have very different possible compositions, okay? Here you may have in the cool side, you may have mainly molecular nitrogen or methane. When you go up in temperature, you may start to have, and because you vaporize, you may have water and CO2. So these are the usual suspects you may have in secondary atmospheres, okay? So I just played a little bit with plausible compositions for these secondary atmospheres that you have here. And here is the same. Basically, the dotted lines correspond to the case when you don't have into account this self-consistency, and the solid when you do the self-consistent model, okay? And basically, the message from this is that when you have in your secondary atmosphere, again, water or CO2, you may not have any difference because these two guys will control much the temperature of the atmospheres. While in those cases in which this water or CO2 are not very important in the atmospheres, then you may expect very big difference. For example, let's look to the case when you have a nitrogen-oxygen atmosphere. You have, if you don't, this atmosphere in principle, because these two guys are very transparent, the temperatures will be super high in the upper layers. But if you start to take into account the chemistry, then these two guys will start to produce nitrogen oxides that start to be more opaque in the infrared and will have a big impact on the temperature, okay? So depending on the exact composition of the atmospheres, you may have that this effect of interplay between chemical composition and temperature will be very important or not. So basically here is what I told you. In this case, for example, nitrogen and methane, you have that methane and nitrogen are chemically processed, and then you have different hydrocarbons that have an impact because they have different opacities and they have an impact on the temperature. And in the other case, you have this case on nitrogen and oxygen that chemically they are processed to produce some nitrogen oxides that they are indeed opaque in the infrared and have an effect on the temperature, okay? Okay, so I just warning message, the codes, there is one code that are publicly available, one to compute the chemical equilibrium composition, and the other is the one I talked to you about this self-consistent calculation of the chemical composition and temperature. Okay, they are in the GitHub. And the last question I wanted to talk to you about I was wondering myself how robust or how reliable are these chemical models, because at some point the idea is to compare the abundance predicted by the models with the abundance retrieved from observation. So it's good also always to have an idea of what are the uncertainties in both type of quantities to evaluate whether the agreement is satisfactory or not. So on the observational side, you may have these uncertainties coming from the retrieval analysis, and these are depending a lot on the study. They may be very large, but on the chemical modeling side, there were not really evaluations of how uncertain are these abundance. So the way to answer it, basically, when I was building the chemical network, I assigned an uncertainty to each reaction. Okay. So basically, there were three categories: the very good known reactions, class A, which had been studied experimentally. I assigned a factor 2 in the rate coefficient. For the worst, for which there is no information and we have just a guess, I assigned an order of magnitude of uncertainty in the rate coefficient, and in between, for those reactions for which we have some information from theory, I assigned an uncertainty in between. Okay. So the core of the idea is to run many models in which you vary randomly the rate coefficients according to the uncertainty of each one. So using a log normal distribution. So here, for example, this is the rate coefficient expressed here in the logarithmic scale for 3,000 runs. So the values that it takes that are randomly varied. So at the end, you have this kind of Gaussian distribution in which the full width at half maximum is the uncertainty that we assign to this rate coefficient. Okay, so you do this for all the reactions, and you do run many models in which these rate coefficients are varied randomly within their uncertainties, and at the end, you may have an idea of what is the uncertainty in the abundance. Okay. So basically, when you do these many runs, you have this dispersion of abundance. So the abundance in this example for CO2, depending on the run in which the rate coefficients are different, varies that large. And from this, it's straightforward to get the mean and the standard deviation, which is this one. Okay. So here we have a first estimation of the uncertainty of the abundance for CO2, and you can see that in the bottom atmosphere, the error is almost zero. There is no error. And this is because chemical equilibrium is controlling the abundance of this guy. And when you start to go up, these equilibrium processes and chemistry start to be important. And then you may have this uncertainty, this error in the abundance. So in this case, it's even less than a factor 10. Okay. And this is for the rest of the species. And here, well, first, the interesting part of the atmosphere is the one that is accessible by observations, which basically is this part here, the shadow wet one. And you see here that there are some species, like for example, on that side, water and CO, for which the uncertainty, the abundance is almost zero. So it's like super accurate, I would say. And others, which like HCM, for example, the gray one, you may have errors or the order of a factor 10, one order of magnitude. Okay, so this is all, again, very molecule dependent. There are molecules for which they don't care about whether the chemistry is very good, poorly known or not. And there are others which have very, very uncertain values. Okay. So from this exercise, also an interesting thing that can be done is that in principle, these error bars, in principle, can be reduced if you know better which are your reactions. If you characterize better the most important reactions, and they are better studied, and the rate coefficient is measured over temperature, then you should be able to reduce these error bars. Okay, and for doing that, the thing you have to do is to identify which are the most important reactions. And the way to do that is to do some kind of correlation between what is the correlation between the reactions the variations in the rate coefficients of the reactions and the variation in the abundance. So the variation in the input, there is the rate coefficient, and the variation in the output. So you find correlations between the certain reactions and certain species, and you may have at the end what are the main reactions that affect your target molecule, okay? So doing this kind of exercise, you may end up with a ranking of most important reactions. In which basically, well, the size is not very large, so you can see much, but basically here you can identify which reactions are worth to study to improve the accuracy of chemical models. So in the upper side, the most important, you have some reactions involving sulfur, which we have seen before. For example, you have sulfur plus OH, which is forming SO, and it's very important to produce then SO2. So you have certain reactions for which the rate coefficient is not very well known, that a better study of its rate coefficient would improve our knowledge of the chemistry of these guys, okay? And also there are some, basically here, the main reactions that appear are reactions for which they are very poorly known. Okay, for example, here in the photoreactions, there are several reactions for which the cross section is not known at all, mainly for some radicals because are very difficult to study in laboratory. So, and they have an important impact on the models. Okay. And I think I am done with these conclusions. So basically from this, what I would like to stress here is that chemical equilibrium is a very good starting point for most exoplanet atmospheres. It's a super good approximation in very hot ones, and it's still a good starting point for cooler ones, okay? That molecules produced by photochemistry, we are just starting to prove this by observation. So I'm sure that in the next years, there will be more examples of molecules produced by photochemistry. So we just need to wait a little bit. From the horizontal mixing, the main conclusion is that the composition is very much homogenized in longitude, so you don't expect to see much differences in the chemical composition in cooler planets, and you may see that more in hotter planets, okay? Then about the interplay between temperature and chemical composition, you don't expect much interplay as long as you have water and CO2 as the main and dominant species in your atmosphere. When you don't have this, then you may expect very interesting effects that disequilibrium may control the temperature. And regarding the uncertainties in the abundance of the chemical produced by chemical models, I was surprised to see that they are not that large. They are always below 1 order of magnitude. I was expecting much more. So I would say that the models are relatively confident, and the exact error depends a lot on the molecule. There are molecules which are very accurately predicted, like water, CO, etc., and others like SO2 or SEN that have more uncertain abundances. And that's all. Thank you for your attention. Yeah.
Okay, thanks a lot for the very interesting talk. Are there any questions also from the Zoom?
Hey, Marcelino, is the rule about the impact of the chemistry disequilibrium onto the temperature profile of the atmosphere? Is it the same rule true with the horizontal quenching? You show us two different patterns. Is there any feedback of the horizontal quenching on the atmospheric structure you expect? Or is the same rule, meaning that it's dominated anyway? So because you show us the structure of the planets is varying with radius, of course.
Yeah.
So you expect your two models, your pseudo 2D, have an impact on the structure that way?
I would say that yes, in principle, horizontally, you should have this quenching of the abundance, so they will tend to be uniform. But as long as you have this main absorbers that control the temperature, that like water or CO2, very abundant and dominating, they will. I would not expect much differences in the much importance between the disequilibrium chemistry and the temperature. Yeah.
Thank you for your really interesting talk.
Thanks.
For the calculating the red coefficient, you mentioned that you run different models. What do you mean by different models? You mean different temperature? Is your model or different type of models that you
When I was doing this exercise of evaluating the uncertainties, you mean?
Yes.
Different models are the same model, but in which you vary the rate coefficients of the reactions randomly according to a log normal distribution. So this is what I mean by different models. So they have all the input exactly the same. The only difference is that you vary the rate coefficients according to the uncertainties. And then you see the impact on that, or from that on the abundance.
Okay, thank you.
Okay.
Hello, thank you for your talk. I have a question again related to the horizontal mixing.
Okay.
Your model has been applied using Jupiter in the equatorial belt mainly, or was designed to that. But my question was about the possible differences in latitude in the planets.
Yeah.
Because of the differences in the angular
Yeah.
speed.
Yeah. That is clearly a limitation of the model, that you cannot describe properly the hydrodynamics. And yeah. So I mean, I would say that that the model should be a good approximation for the equatorial regions, but perhaps not for the polar ones, let's say. Yeah.
Oh, hi, thank you. So based on the first point, I guess the chemical equilibrium is not a good approximation for cold planets and Earth-like planets, right?
Yeah.
So what is the proper way to model their atmosphere chemistry?
So, I mean, it's a good approximation, because even here in the Earth, you compute what will be the chemical equilibrium composition for an atmosphere with nitrogen atoms and oxygen atoms. You may end up that the bulk, the core of the composition is nitrogen, molecular nitrogen and molecular oxygen. So it's a good, let's say, it's a good starting point to have an idea what will be the bulk composition of the atmosphere. But if you are worried about the details, that sometimes may be the ones that will be observed later on, then you have to include the disequilibrium processes. So mixing, vertical mixing, horizontal mixing if possible, and photochemistry. So I would say that at least you should include the vertical mixing and photochemistry, because this will, for the cool planets, in principle, the chemical reactions, as you go down in temperature, chemical reactions become slower. So there are more chances that other processes come to control dynamics, or photo processes come to control the composition. So in principle, I would say that you need a non-equilibrium model, at least including photochemistry and vertical mixing.
Okay, I have one more question. So considering these like quenching effects and photochemistry, are they like their calculation are based on the modeling of chemical equilibrium, and we just add modifications to this equilibrium network, or it's they need to be calculated in a different framework?
So if I understand correctly, so basically chemical equilibrium is like, in these models, is the starting point, so the time zero. You compute the composition of the atmosphere at chemical equilibrium, and this is your time zero, and then you let it evolve, including all the time-dependent effects, let's say, which are chemical reactions, photodissociations, and mixing processes, and you let it evolve until you reach a steady state, and then you assume that your steady state is the one that best describes your atmosphere. I don't know if I answered your question.
Okay, so the chemical disequilibrium is still a stable state, a stable condition, right?
Yes, in
Okay.
principle, as long as you don't have any other process affecting the atmosphere from the surface or from outside, I would say that the atmosphere should be in a stable state, a steady state.
Okay, we have a question from Zoom. Let me see if I can see it. It's what is the best way to estimate the strength of vertical and horizontal mixing for the different planets?
Okay, so this is one of the uncertain points from the models because typically they have been for solar system planets they have been inferred from observation. So basically, in the example I showed before, you observe, for example, the abundance of CO in Jupiter, and then you from this observed abundance you determine which will be the quench level, and then you find which is the best mixing strength that describes this quench level. Okay, so you do like you infer that from observations from solar system, but you cannot do that still for exoplanets. So for exoplanets, they are coming from global climate models. So basically, these global climate models can give you an estimate of what are the different mixing processes, and then you infer that from that. But this is I would say a very critical and uncertain point of models. And in fact, many models, what they do is that they vary a lot this mixing strength to see what is the impact on the abundance, because we are aware that this is not very well constrained parameter.
Thank you for the talk. Just one question. So the examples that you showed are mostly the objects that are in the yellow strip of this condensate molecules, ionized material. So do you take also condensates in the disequilibrium computations into account?
If these condensates are taken into account in the chemical equilibrium calculations, you mean?
Yeah.
Yes, in principle, yes. Also, from a numerical point of view, sometimes it may be tricky to take into account properly all of them. So sometimes what you do is you just include one and see what is the temperature at which it condenses. But in principle, yes, you can. In fact, this transition or this condensation temperature is calculated this way with these chemical equilibrium calculations. So this is the temperature at which, for example, scandium will start to condense in some scandium oxide or whatever.
And the code that you showed, I mean, on GitHub is supporting condensates as well?
The color?
The code that you gave link in the GitHub.
Condensates are taken into account in these chemical equilibrium calculations, but not yet in the disequilibrium ones. That is something I would like to do, because there are like several ways to approximate that, because it's very difficult to describe that properly, because to describe that properly, you will have to take into account which are the individual microscopic processes that may start to form some condensate from gas phase particles, which is right now is not well known, which are the individual reactions that they start to form first clusters and then they grow and stuff like that. So they like different approach to the problem. So it's something that for cooler planets is very important, because you expect clouds and they are observed.
One very short question. So when you compute photoreactions, do you also take into account the uncertainty of the incoming flux from the star? I mean, how well do you need to know this light coming from the host star?
No, in these models, but you could. I don't know what is the level of uncertainty from the for the stellar spectrum of these stars that host exoplanets. In principle, you have an idea. No, in these models, I didn't take into account that. I just focus on the uncertainty that is arising from the poor knowledge of the chemistry, I would say. But you can do this exercise with any parameter, any input parameter that you consider that could be uncertain. But yeah, I mean, that could be done. But I'm not very very aware of what is the level of uncertainty in this. I would say that there is large for the UV part. I think there is. I guess that it is very poorly known what is the UV flux of these stars.
Okay.
Any final question? From Zoom also it's covered, right? There are no other. Okay, so I see there's a lot of interest in the topic. So just to say, Marcelino is staying with us until December, right?
Until Christmas, yes.
Until Christmas. So if you would like to discuss with him some topics, he is in the GTC building. So he's very nice, as you can see. So you can visit and talk to him about models, or if you want to use this code. So I really encourage you to like make connection and go talk to him if you would like to. And with this, I think we thank Marcelino again and we finish. Okay. And the students come here, remember to sign for the attendance.
Thank you. Okay. Yo dejo de compartir, vale. Gracias, complicada, ya se conoce tanto con alguien y aquí todo lo necesario.